Thanks, Alex. On behalf of OEHA, I'd like to welcome you all to today's webinar on PFOA and PFOS toxicology and epidemiology data. We're really excited about today's webinar. We have great participation, and we're looking forward to hearing from you all. OEHA is a department within the California Environmental Protection Agency, and we're the lead state agency for assessing health risks posed by environmental contaminants. And in this role, we provide health-based recommendations to state agencies to inform their actions to reduce risks from environmental contaminants. So this webinar falls at the start of the process to develop public health goals for drinking water for PFOS and PFOA. A public health goal, or a PHG, is the concentration at which drinking water is not expected to result in significant health effects to lifelong consumers of the water. OEHA is developing these health-based concentrations at the request of Cal EPA's State Water Resources Control Board, who will consider these PHGs as it develops its drinking water standards for PFOA and PFOS. With regard to the PHG process, we initiated the PHG process at the beginning of this month and are now in the data call-in period. We hope this webinar will spur people to provide information they would like us to consider that we're not already aware of. The data call-in period closes early next year on January 15th, and we'll be providing you information about how you can provide data to OEHA as part of that data call-in process shortly. To quickly touch on other parts of the PHG development process, once we develop a PHG proposal, we release the underlying assessment for public comment and workshop, followed by formal scientific peer review. After consideration of this input, a second draft is released for comment. The proposal and analysis is further then refined, and a final draft is released, along with a document indicating how the public and scientific peer review comments were addressed. Okay, so turning to today's activities. We've done a lot of prior analysis of the health literature and data on PFOS and PFOA, and this was in order to recommend drinking water notification levels to the State Water Board for these compounds. We released these recommendations last August. If a drinking water concentration is provided to consumers is greater than a notification level, the Water Board recommends that the water utility inform its customers and consumers about the presence of the chemical and about health concerns associated with it. Dr. Chris Banks and Dr. Anatoly Socialov from OEHA are going to present and start the workshop by discussing the experimental data and analysis behind our notification level recommendation. Following their presentation, there will be 10 to 15 minute period for asking questions. So while we were developing the notification levels, a critical body of data became available. The National Toxicology Program released data from a high-quality chronic toxicity and carcinogenesis study. We're fortunate to have presenting from the NTP offices in North Carolina, Dr. Chad Blystone and Dr. Ronald Herbert. They'll be presenting on study design and the pathology review process underlying the data for this study. There'll be an opportunity to ask questions about the study following their presentation. And that image that was up on the right-hand side of the screen was from the NTP's website and listing the various data sets, well, providing an example of the various data sets that are available on that study. One of the potential toxicities of concern for low-level exposure to PFOS and PFOA is immunotoxicity. And we're fortunate to have Dr. Annie Rooney from the NTP present on NTP's 2016 comprehensive review and characterization of immunotoxicity associated with PFOS and PFOA. Dr. Rooney will also be available to answer questions about his presentation following his presentation. So then we'll take a brief 10-minute break and start up at 11 a.m. Pacific time to hear from Dr. Craig Steinmaus of OEHA about the human data available on PFOS and PFOA. And then his presentation will be followed by a brief Q&A where people can ask questions of Dr. Steinmaus. Then we'll have roughly a half an hour for general Q&A where webinar participants can ask questions of OEHA. So as you're listening to these speakers, feel free to send in questions using the GoToMeeting box as Alex has just described. So again, I want to thank you for joining us. On your screen, you can see how you can provide information to OEHA regarding the PhD process, and the moderators will be going into this in a little bit more detail at the end of the presentations. I'm now going to turn the webinar over to today's moderators, Dr. Elaine Kahn, Chief of OEHA's Water Toxicology Section, and Dr. Melanie Marty, OEHA's Assistant Deputy Director for Scientific Programs.
Thank you, Lauren. Good morning, everyone. Today's webinar is being held in connection with the initiation of the Public Health Goal Development for PFOA and PFOS. And this includes a data call-in for these chemicals, as Lauren had mentioned. So what we're going to cover today first is the data that were evaluated in developing OEHA's notification level recommendations for PFOA and PFOS. But we'd like to build on that, and we'd like the stakeholders to provide us with any data or information that may be helpful in informing the risk assessment for these PHGs. With that, we'll start today's presentations with Dr. Chris Banks and Dr. Anatoly Sokolov, who are both staff toxicologists in the Water Toxicology Section at OEHA. Dr. Banks received his PhD in environmental toxicology from UC Riverside, and Dr. Sokolov received his PhD in biochemistry and molecular biology from UC Davis. They'll be speaking to you about the experimental data reviewed for the notification level recommendations for PFOA and PFOS. So, Dr. Banks, over to you.
Thank you, Dr. Kahn. So hello, everyone, and welcome to the webinar, and thank you all for joining us this morning. So today I'm going to talk about the data we evaluated to derive the notification level recommendations for PFOA and PFOS. Okay. So here are the structures of PFOA and PFOS, the usual suspects when dealing with per- and polyfluoroalkyl substances, collectively known as PFAS. So PFOA and PFOS are the best studied of the PFAS. And as I'm sure many folks are aware, these chemicals were used in many consumer products due to desirable properties such as water and stain resistance. These chemicals are very persistent in the environment, and they have long biological half-lives, so they bioaccumulate. And results from the state's Biomonitoring California program report that PFOA and PFOS are found in 98 to 100% of the participants in all the different cohorts they've examined. So it's safe to say that Californians are being exposed to these chemicals. So at the start of our process, OEHA evaluated risk assessments of PFOA and PFOS done by other agencies, including the United States Environmental Protection Agency, the State of New Jersey's Drinking Water Quality Institute, the National Toxicology Program's monograph on immunotoxicity, the Agency for Toxic Substances and Disease Registry's draft report on perfluoroalkyl substances, and any other reports we could get our hands on. These documents served both as good starting points for us in our assessments, both for looking at toxicity evaluations and as a source of toxicity studies. And to build off of these assessments, OEHA did a focused literature search to identify any new studies published after these other risk assessments were completed. So basically from 2016 to the present. Additionally, in late 2018, the National Toxicology Program released the data from their chronic toxicity and carcinogenicity bioassay of PFOA. And so those data were available to us for our evaluation. Here is a general flow chart describing how we did the assessments for the notification levels for PFOA and PFOS. We started with a focused literature search looking at studies published since 2016. Studies published before 2016 were covered in the assessments that we had evaluated previously, and the focus was on newer literature. Animal studies and human epidemiology studies were evaluated separately, and Dr. Craig Steinmaus is going to talk to you a bit later in this symposium about the human data. And we also looked at mechanistic data, but for the animal studies, we focused on known toxicity endpoints of PFOA and PFOS, namely liver toxicity, immunotoxicity, reproductive toxicity, thyroid toxicity, and cancer. And ultimately, it was cancer, liver toxicity, and immunotoxicity which drove the notification level recommendations. I will point out that similar effects are being evaluated in the human literature as well. Okay, here is a brief summary of the animal toxicity studies since 2016. And I do want to mention that these studies here add to the large volume of available literature published before 2016. So the numbers of studies here are just sort of the tip of the iceberg, most recent studies that we've seen. For liver toxicity, we looked at 16 studies and saw many different endpoints, including increased liver weight, increased levels of liver enzymes in the serum, hypertrophy, which is increased cell size, cytoplasmic alteration of hepatocytes, necrosis and apoptosis, which are terms for describing cell death, changes in lipid homeostasis, and other effects. It is clear that the liver is a major target for PFOA, and many different liver toxicity endpoints were reported. For immunotoxicity, we looked at 7 studies and saw various toxicity endpoints, including changes in spleen and thymus weight, changes in cytokine levels, cytokines being cell signaling molecules associated with the immune system, reduced antibody response, and other effects. For the thyroid, we looked at 5 studies which reported changes in thyroid weight, follicular cell hypertrophy, and changes in thyroid hormone levels. And this is important because the thyroid regulates many different physiological processes through the release of hormones. We looked at 10 reproductive toxicity studies which reported adverse effects on the testes and sperm in males, developmental effects such as embryo and fetal loss, and changes in sex hormone levels in both sexes, among other things. And PFOA is listed under Proposition 65 based on developmental toxicity effects. The candidate critical studies were thoroughly evaluated, and the most suitable study was selected. And for the PhD, we will update our literature search, and we will look at all relevant toxic effects, such as neurotoxicity or cardiotoxicity, basically whatever data we can find. So the critical study for PFOA that we selected was from Lee et al. 2017. And this study looked at hepatotoxicity in male and female BALB/C mice. And in this study, mice were given several doses of PFOA via oral gavage for 28 days. We determined a lowest observed adverse effect level, or LOEL, of 0.05 milligrams per kilogram per day based on several liver effects, including changes in mitochondrial membrane potential, increased apoptosis, oxidative DNA damage, increased liver weight, hypertrophy, and lipid accumulation in the cytoplasm. So the changes in membrane potential, increased apoptosis, and oxidative DNA damage in the liver were observed at all doses. I do want to mention here that serum concentration is a better dose metric than administered dose for point of departure determination. And I just want to say a little bit about what the point of departure is. So the point of departure, or POD for short, is the point on a dose response curve that corresponds to a low effect level or a no effect level and serves as the starting point for determination of maximum acceptable doses, which are often called reference levels or reference doses. So anyways, serum concentration is a better dose metric than administered dose because of the big differences in half-life between rodents and humans. And the serum concentration reflects the amount of compound directly available to internal tissues. So the LOEL of 0.05 milligrams per kilogram per day corresponds to a serum concentration of 0.97 milligrams per liter in female mice. So in males, the value was 1.2 milligrams per liter. So basically, males and females had the same value. But we did go with the female value of 0.97 milligrams per liter as the POD, since it was slightly lower. Toxicokinetics are very important, and this is an area of great interest to us. And on that note, I'm going to hand the talk over to Dr. Socialov, who will discuss toxicokinetics in more detail.
Thank you, Dr. Banks. As Dr. Banks mentioned, PFOA and PFOS have the ability to bioaccumulate, and these properties are different among species. The ability of a chemical to bioaccumulate can be described by its half-life. Longer half-lives correspond to a better retention of the chemical in the body. From the following table, we can see that the half-life in human is much higher than in mice or rat. Therefore, for the same amount that humans consume compared to animals, higher serum concentrations would be observed. We also see some sex differences for example, female rats with 2 to 4 hours half-life are much faster eliminators of PFOA than male rats. These differences, as well as the overall long retention of PFOA and PFOS, could be explained by the kidney reabsorption pathway, which is the main factor in the overall toxicokinetic mechanism of absorption, distribution in the body, and elimination for these compounds. Knowing the specifics of this toxicokinetic process, we can predict the serum concentration for a given study and applied dose. And specifically with PFOA and PFOS, serum concentrations are the preferred metric for interspecies extrapolation that Dr. Banks will describe later. However, when the study already reported serum concentrations, we don't necessarily need such adjustments. All right, next slide. In case we come across a study that did not report serum concentrations, we can apply a physiologically based pharmacokinetic or PBPK model in which we imagine the simplified body as a series of toxicokinetically important compartments connected by blood flows with additional absorption and elimination components. The compound levels in the compartments and transitions between compartments are then mathematically described by differential equations, and the computational solution of this system of differential equations would predict various internal metrics such as the serum concentration of the compound or its concentration at the target organ. Here we see an example of a PPK model for P4 in mice, and you can see the pathway of renal reabsorption from the kidney filtrate compartment to the renal plasma compartment that drives the overall toxicokinetics of P4 in mice. So far, we have looked at several PPK models for different species, with selected examples presented in the tables for mouse and human PPK models on the right. Right, next slide. Several models were evaluated, and this is an ongoing project. However, due to reported serum concentrations in the chosen critical studies, we did not need to apply these complex models to derive serum concentrations from the applied doses. Therefore, in this case, PPK models were not used. However, it is possible that in the future additional studies or with additional considerations, we will have to use such models. Therefore, we will continue to validate the relevant rodent and human PPK models, and we welcome additional information in this area. In our risk assessment process, we derive target serum concentrations from the animal point of departure serum concentration, and next, we derive the corresponding human oral dose. As I've shown in the previous slides, multiple human PPK models are available for this task, which is transition from the human serum concentration to human dose. However, due to very long half-lives PFOA and PFOS pharmacokinetics in humans can be approximated by a very simple one-compartment model. This approach has been used by the US EPA and involves calculating a clearance factor. We use the same approach for the notification level derivation. Back to you, Dr. Banks.
Thank you, Dr. Socialov. Okay, so we first calculated the target human serum concentration by dividing the point of departure with uncertainty factors. And if you're not familiar with the general risk assessment process, uncertainty factors are adjustments that we make to account for differences between animals and humans and differences among people, as well as other sources of uncertainty to get to an exposure level where there is no effect. So we use a total uncertainty factor of 300, which is comprised of root 10, which is basically 3, for differences between animals and humans, 10 for differences among people, root 10 because the lowest dose produced an adverse effect, and root 10 to account for potential reproductive toxicity at a level below the POD. So there was a gestational study in mice, Van Estrik et al. 2016, that reported transient reductions in pup body weight on postnatal day 4 following gestational exposure at a lower administered dose than the Lee et al. 2017 study. However, the Van Estrik study did not measure serum concentrations, so we did not select this study as a critical study. I want to point out that there was no adjustment to account for the short duration of the study, because even though the severity of liver effects may increase over time, these early manifestations of liver toxicity do not appear to increase in magnitude with longer exposures. So, using a POD of 0.97 milligrams per liter and a total uncertainty factor of 300, a target human serum concentration of 3.2 micrograms per liter was determined. The acceptable daily dose was then calculated by multiplying the target human serum concentration by a human clearance factor derived by the US EPA in their PFOA assessment. The clearance factor is the estimated rate of PFOA clearance from the body, and this gives us in total an acceptable daily dose of 0.45 nanograms per kilogram per day. The non-cancer reference level was then derived by multiplying the acceptable daily dose by the relative source contribution and then dividing by the drinking water intake rate. We used a relative source contribution of 20%. The relative source contribution is an estimate of how much exposure comes from drinking water, and because we anticipate that people are exposed to PFOA from many sources, including food and indoor dust, we set the level at our default of 20%. For the drinking water intake, we use a lifetime weighted average of 0.053 liters per kilogram per day, which was derived by WEHA in 2012 and approved by the Scientific Review Panel. So we know that US EPA updated their exposure factors handbook recently, and their drinking water values are actually quite similar to ours. Both drinking rates account for the fact that infants and children drink a lot more than adults on a body weight basis. So using these values, a non-cancer reference level of 2 parts per trillion was determined. So for cancer, we evaluated these 4 studies listed here, including the National Toxicology Program bioassay data, which were made public at the end of 2018. The Butenhoff et al. 2012 study reported testicular Leydig cell adenomas in rats from chronic dietary exposure to PFOA. Beagle et al. 2001 also reported testicular tumors, and additionally liver and pancreatic tumors in rats chronically exposed via the diet. However, this study only used 1 dose and a control. The Filgo et al. 2015 study exposed pregnant mice via drinking water, and then the pups were followed for 18 months. And these pups had a higher incidence of hepatocellular adenomas. And lastly, the NTP study reported significantly increased incidences of hepatocellular adenomas and/or carcinomas, and pancreatic acinar cell adenomas and/or carcinomas in male rats following 2 years of dietary exposure. And so there's definitely some consistency in the endpoints observed from these 4 studies. So here are the NTP tumor data, and if you look at the column on the far right, that's for pancreatic tumors, you can see that the pancreatic tumor data is really prominent here, and there's a huge increase in tumor incidence even at the lowest dose. The liver tumors were also significant at the mid and high dose. And I do want to mention that here we used an effective number of animals, so we removed animals that died before the first appearance of the first for the appearance of the first tumor from our analysis. Okay, so we did a dose response assessment using US EPA's benchmark dose software to do a multi-site tumor analysis for both the liver and pancreatic tumors from the NTP study. We determined the multi-site BMDLO5, which is the lower 95% confidence limit of the dose at the benchmark response of 5%. So that is a dose estimated to produce a 5% increase in tumor incidence over baseline. And this value was 0.648 micrograms per kilogram per day. We then applied body weight scaling to the 1/8 power to account for toxicodynamics differences between animals and humans, and this is usually around a factor of 2 or so. WEHA normally does the scaling to the 1/4 power, but because toxicokinetic differences were already accounted for by utilizing serum concentrations as the dose metric, the full factor of 1/4 was not considered necessary. Then the cancer slope factor was calculated by dividing the benchmark response at 5% by the BMDLO5 from humans, giving us a slope factor of 143 per milligrams per kilogram per day. Then the cancer reference level is determined by dividing the risk level by the product of the slope factor and the drinking water intake. So in this case, the risk level is 1 in 1 million. And this gives us a final cancer reference level of 0.1 parts per trillion. So I will note that age sensitivity factors were not included in this calculation. So WEHA normally uses default age sensitivity factors to account for the fact that developing organisms are generally more susceptible to chemical carcinogens than adults. But in this case, NTP ran a parallel study to the 2-year bioassay where rats were also exposed during gestation, and there weren't any significant age-related differences in terms of tumor induction. So with PFOS, we saw many of the same endpoints as we did with PFOA. So since 2016, there were 10 liver toxicity studies, 3 immunotoxicity studies, 3 thyroid toxicity studies, and 7 reproductive toxicity studies. And a selection of the observed toxicity endpoints are listed here. And like PFOA, PFOS is listed under Proposition 65 due to developmental toxicity. So once again, these studies add to the large volume of available literature published before 2016. The candidate critical studies were thoroughly evaluated, and for the PhD, once again, we will update the literature search and look at all pertinent toxic effects. So the Dong et al. 2009 immunotoxicity study was selected as the critical study. And in this study, mice were given various doses of PFOS via oral gavage for 28 days, and immunotoxicity was observed at all doses but the lowest one. A NOAEL of 0.008 milligrams per kilogram per day was identified based on decreased plaque-forming cell response, which is a measure of antibody response to an antigen. And this NOAEL corresponds to a serum concentration of 0.674 milligrams per liter. Using the same methods for PFOA, a non-cancer reference level of 7 parts per trillion was determined by using a total uncertainty factor of 30, which is comprised of 3 for differences between animals and humans, and 10 for differences among people. A clearance factor determined by US EPA, and our lifetime average drinking water rate. And the details of this calculation can be found in the technical support document for anyone who may be interested. Okay, for cancer, there was only the Butenhoff et al. 2012 studies available for analysis, which was published based on the 3M Tomford 2002 studies. And in these studies, PFOS was administered in the diet for 2 years to male and female rats. In male rats, there was a significant increase in hepatocellular adenomas at the highest dose and a positive trend for pancreatic islet cell carcinomas. Female rats also showed an increase in hepatocellular adenomas as well at the highest dose. So I do want to note that the highest dose in this study is right around 1 milligrams per kilogram per day, which is the lowest dose that was used in the NTP PFOA 2-year bioassay. So one could speculate that higher doses of PFOS may lead to a greater tumor incidence. So even though the Butenhoff studies were the only PFOS carcinogenicity studies, we evaluated the cancer potency, stating that PFOS is being evaluated as a carcinogen because of the positive animal carcinogenicity bioassay data from Butenhoff et al. 2012, and because of the similarities in chemical structure and biologic activity between PFOS and PFOA. So both chemicals have very similar structures in that they're both perfluorinated 8-carbon linear molecules, and the non-cancer biological activity was also very similar. Similar endpoints were reported for both chemicals, and with the totality of carcinogenicity data for PFOA, a cancer analysis for PFOA is supported. Using the same methodology for PFOA, we calculated a cancer slope factor of 45.5 per milligrams per kilogram per day, and ultimately a cancer reference level of 0.4 parts per trillion. Okay, so this slide shows the final values reported in the notification level document. For non-cancer effects, we have reference levels of 2 parts per trillion for PFOA based on liver toxicity in mice, and 7 parts per trillion for PFOS based on immunotoxicity in mice. For cancer, we have reference levels of 0.1 parts per trillion for PFOA based on increased liver and pancreatic tumors in male rats, and 0.4 parts per trillion for PFOS based on increased liver tumors in male rats. However, because the reference values are below the level of detection, OEHA recommends setting the notification level at the lowest levels that can be reliably detected in drinking water using currently available and appropriate technologies. And this corresponds to 5.1 parts per trillion for PFOA and 6.5 parts per trillion for PFOS. Okay, and I just want to quickly acknowledge all the different folks who have contributed to this project, and I am happy to answer any questions that any folks may have. So thank you very much.
Great. Thank you very much, Dr. Banks and Dr. Socialoff. Now we're going to start taking questions from the audience, and I will start with the easiest one, which is, will the slides be available? And yes, they will be, and so will a recording. As soon as we get these things organized, we will send a follow-up email to let participants know where you can access these slides and the recording of the presentation as well. So now to the serious questions. We have one from Lisa Corey, and she asks, why is the OEHA drinking water intake used for the notification level recommendations different than used by OEHA for other purposes? For example, for perchlorate or trihalomethane PHGs and other states' PFOA and PFOS drinking water standards, for example, New Jersey's. And she continues with, for example, using the drinking water rate used with the perchlorate For THM-PHGs, the PFOA cancer reference level would be 0.2 parts per trillion, and the response level would be 20 parts per trillion, rather than the recommended 0.1 part per trillion and resulting response level of 10 parts per trillion if the Division of Drinking Water uses its historical convention. So we did not use anything different from what we had used in the THM's PHG or perchlorate in terms of how the drinking water intake rates were derived. But for perchlorate, we did use specifically an infant drinking water intake rate, whereas for this assessment, we used a time-weighted lifetime average drinking rate. And for the THMs, we did take into account exposure via inhalation and dermal exposures as well during showering and bathing and other household uses of tap water. So you will see some slight differences, but we do derive all of our drinking water intake rates from our own OEHA 2012 analysis that was peer-reviewed by the state's scientific review panel. So although you see a few slight differences, these numbers were peer-reviewed, and that's where the main differences lie. And we have another question from Lisa Corey.
This is Melanie Marty. Since this assessment did not include a systematic literature review, including risk of bias analysis, how does OEA ensure that the point of departure is reflective of sound scientific studies and the overall weight of the evidence? So in terms of systematic review, first of all, the earlier assessments that OEA reviewed, those by NTP, US EPA, et cetera, did conduct systematic reviews. So that's kind of our basic data set that we were looking at. We did search for additional studies, which you heard Dr. Banks mention, and we also thoroughly evaluated those studies for consideration in developing recommendations to the Water Board for the notification levels. So I might point out that, for example, the Dong et al. Was part of, which was the immunotoxicity study, that was part of NTP's systematic review.
Okay, next question comes from Lanaya Vols-Alexander.
Okay, what about the 2018 NTP study caused OEA to select it over the other studies reviewed as the basis for the PFOA cancer reference level and as supporting study for the PFOS cancer reference level? So this study was an NTP study, which are widely viewed as the gold standard for carcinogenicity bioassays. It was extremely well conducted. The data you will hear in a moment from the NTP folks themselves, those data were reviewed via NTP's rigorous process looking at the pathology so that they can be sure what they're seeing is what they're seeing. So, and in fact, it is the most sensitive study of PFOA carcinogenicity to date.
Okay, next question is from Emily Calderon. Other states, for example, New Hampshire, Michigan, and Minnesota, have used a higher relative source contribution, or RSC, of 50% using empirical data rather than the 20% default used by OEHA. Does OEHA plan to reevaluate the RSC and use PFOA, PFOS exposure data to define the RSC? For example, using the RSC of 50%, the PFOA non-cancer reference level would be 4 parts per trillion, and the response level would be 40 parts per trillion rather than the recommended 2 parts per trillion, which would result in a response level of 20 parts per million if the Division of Drinking Water uses its historical convention. And yes, we will reevaluate this RSC, and we would appreciate any additional information that anybody thinks would assist us in this evaluation as part of this data call-in. Okay, another question from Emily Calderon.
Why did OEA use this study that allowed the lowest possible point of departure dose rather than choose the study with the highest quality? Okay, I'm not totally clear on that question. Since we use different studies for different points of departure, but we chose the studies that we thought were the most sensitive and were high quality.
And the next question is from Helen Gaden, and she asks, why was body weight scaling, not TK differences, used for the cancer calculations?
I guess I'll answer that. We actually used 1/8 power of body weight scaling to account for possible toxicodynamic differences. Using plasma concentrations, we considered that accounting for toxicokinetic differences. So when we consider interspecies uncertainty factor, where we usually, in case of cancer, let's say when we consider a body weight scaling to account for differences between species, that is combined of the two factors. So we did account for toxicokinetic differences in our process. We were just conservative on that side. Back to you, Dr. Han.
Okay, we have a question from Richard Jack. And the question is, we can detect lower than the notification level. Can you consider a lower level if a laboratory reliably demonstrates a limit of quantitation at a lower level?
Okay, this is Melanie. That question really has to be answered by the water board folks. We do the risk assessment piece, and the water board takes it from there.
And we do have
someone here from the water board, Darren Palemas, who has agreed to answer the question.
So when we're considering the levels, we usually contemplate the number of labs that can achieve it. So while certainly some labs can achieve a number lower, we do want to make sure that there's enough laboratories available to do the number and achieve that, as well as in this instance, so the notification levels were set using method 537, revision 1.1. Method 537.1 is a new method that we will allow. It does have lower levels, and eventually we will transition to that, but not all the labs are certified in that one yet. So the levels were picked based on lab capacity.
Thank you for that answer. Unfortunately, we are out of time for this Q&A section. We have to move on to our presentations from the NTP. So if we did not have a chance to answer your question here, hopefully we can get to it at the general Q&A at the end of this webinar.
Okay, up next we have scientists from the National Institute of Environmental Health Sciences Division of the National Toxicology Program, or NTP, to tell us about the NTP study of PFOA, chronic toxicity, and carcinogenicity, both with and without perinatal exposure. Dr. Chad Blystone received his PhD in toxicology from North Carolina State University and is the lead toxicologist on the NTP PFOA chronic and carcinogenicity studies and the NTP PFAS 28-day toxicity studies. Dr. Blystone will be talking to us about the experimental design of the PFOA studies.
All right, thank you for that introduction. We are attempting to advance the slide. There we go. Oh, there we go. Oh, okay, so sorry about that. All right, yes, thank you for the introduction. So the National Toxicology Program has a draft report on the PFOA chronic toxicity and carcinogenic activity, we're referred to as TR 598. And this is currently on our website, and the data that was referred to in the previous talk is incorporated in this report. A little bit of background on NTP technical reports. these generally integrate multiple studies that were run under GLP requirements, GLP referring to good laboratory practices. And in these reports, we provide descriptions of the methods, results, any additional analysis that was conducted, and the NTP interpretation on the data that are within the report. These reports undergo external peer review, typically by a panel of external experts. And for the PFOA draft report, this has been scheduled for December 12th, next month. And so the presentation will provide, this presentation will provide an overview on the design and the pathology peer review methods by my colleague, Dr. Ron Herbert, for this study. And so we won't be talking so much about the results and conclusions, as that will be reserved for the peer review on December 12th. A little bit of background on why this study was conducted. So as mentioned, there have been previous chronic toxicity and carcinogenicity studies. At the time of this study, when it was designed, there were 2 previous studies that were not conducted by the NTP. These were in rats, and exposure started in young adult animals that were 6 to 8 weeks old. However, from several exposure studies, it's been seen that exposure likely occurs throughout life, and which can be potentially impacting in utero development and early postnatal development. And it was due to these concerns of lifetime exposure to PFOA, yet the previous chronic studies started exposure at 6 to 8 weeks old, so the NTP tested the hypothesis that perinatal exposure, which includes gestation and lactation, would quantitatively, in other words, increase the response, or qualitatively lead to a different type of response when compared to animals without this perinatal exposure. So the initial study design, I'm going to refer to as Study 1 here and also in the report, was based on previous studies conducted by the NTP to address this question. What is the early life exposure contribution to ultimate chronic toxicity and carcinogenic outcome? And so in these design studies, I have a figure here over on the right, and the top right here is a example of a typical chronic study where exposure indicated by the black bars here starts post-weaning. And then there is no exposure during the gestation and lactational periods. And the F0 is referring to the adult, or the parent, and the F1 here is referring to the offspring. And so in the report, we denoted this by a 0 of 300 as an example, of the 0 referring to no exposure during this time period, and the 300 referring to the exposure that occurred post-weaning. And within our studies, we had an interim time point for an evaluation of potential ongoing toxicity, and then the terminal evaluation at the end. And so in comparison, we had animals without the perinatal exposure, and then we had animals with the perinatal exposure. So it started with the parents, should say with the maternal exposure of the F0, and then potential exposure during the F1 development in utero, or postnatal, early postnatal during the lactational period. And we refer to this in the technical report as 300/1000. So the 300 would be referring to the exposure during this time period, and then the 1000 be referring to the exposure post-weaning. And so due to observed toxicity in the males during the first study at the interim necropsy, the male portion of the study was stopped, and the males were started at lower exposure levels. And that is referred to as Study 2 within the technical report and in this presentation. But in both studies, the male and female rats, we had N of 50 animals per group. They were exposed to PFOA via feed. This is consistent with human exposure and also with the previous studies. However, we want to note that post-wean exposure differed between the sexes, and this was due to the differences in elimination rates that was alluded to in the previous talk, where females have a faster elimination rate compared to males. And so we increased the exposure levels in females to adjust for this. So essentially, there were 2 types of comparisons that were made during the analysis and interpretation of the data. First, exposed groups were compared to the 0-0 control group. Again, the 0-0 referring to no exposure during the perinatal period or the post-weaning period. So this was considered the true control of the study. And we were looking to see if there was any increase in effects by pairwise comparisons to this control. And then the second analysis and comparisons was looking at the exposed groups and comparing them with and without perinatal exposure to see, again, if there was a quantitative or increased response or a qualitative change, or we see a completely different response with this perinatal exposure. So right here is a table outlining the exposure for perinatal and post-weaning, and this is similar to the layout. I've combined the male and the female groups together here, but we have a similar layout in our technical report of how we analyze and show the data. So over here on the left in red is the perinatal exposure levels of 0, 150, and 300 parts per million. And going across the top here is the post-weaning exposures of 0, 150, 300, and 1,000 parts per million. And the M's and the F's are referring to the males and females. And so in the first study, we had 2 exposure levels of 150 and 300 parts per million. And then, as I noted, the females had a higher exposure to account for the faster elimination and went up to 1,000 parts per million exposure level. And so our comparisons were first to compare all these groups to the control, which is the 0, 0 for each sex. And then we also did comparisons between animals groups that had no perinatal exposure. So, for example, here the 0, 150, and then the 150, 150 for the comparisons with and without perinatal exposure. And then for 300, we did a similar comparison, and then we also did a similar comparison for the females. We're comparing the 0, 300 to the females that had perinatal exposure of 150 and 300. And as I mentioned, at the interim necropsy, we observed toxicity in the males that was considered overt, and that we stopped the study at 21 weeks. So we collected data at 16 weeks, but did not carry them on to terminal evaluation. We restarted the study on a simplified design, as shown here. And again, this is a representation of the data and how it's presented in the technical report. So as you can see here, we had one single perinatal exposure of 300 parts per million. It was simplified because there was minimal effects that were observed at 300 parts per million in our study. And then so we dropped 150 parts per million and focused on just that single exposure and see if we could see a difference. And then the post-weaning exposure of 0, 20, 40, and 80 parts per million were used. And this 20 is noted to be lower than the previous chronic studies in rats. And so similar to the study 1, we did comparisons of all these exposed groups to the 0, 0 control right here. And then we also did pairwise comparisons between animal groups that did not have the perinatal exposure to ones that did. And so we did that for each exposure level, 20, 40, and 80. And then also a comparison between the control of 0, 0 to animals that only had exposure during the perinatal period of 300 parts per million and no post-weaning exposure. So this is providing essentially a broad overview on the endpoints that were evaluated. There are 3 essentially phases or time points that were evaluated. First, there was the perinatal evaluation. So we looked at the dam or maternal body weights, clinical observations, same with the pup body weights. We're looking at their growth parameters. We're looking at littering parameters. Was there an effect on litter size? Was there an effect on parturition or the birthing process? And then additionally to this, we looked at dam and pup plasma concentrations of PFOA on postnatal day 4. This is very important, as alluded to in the previous talk, and to compare to human exposure, we need to have an idea of what the internal levels are, because there's a wide variety of kinetics And so the external dose can vary, or the external dose will lead to a variety of internal doses depending on what species is being used and what sex. And so, in addition to the postnatal day 4 evaluations of dam and pup, we also looked at exposure during gestation within the dam and the fetal concentrations on gestational day 18, and this was all done in the second study. We had the interim evaluation at 16 weeks. The animals were 19 weeks of age. We're looking at body and organ weights for signs of toxicity. We did histological evaluations and clinical chemistry evaluations. Also, additionally looking at plasma concentrations within males and females. And then we did a couple of assessments within the liver, looking at acetyl-CoA oxidase enzyme activity and aromatase enzyme activity to assess potential mechanistic pathways. Acetyl-CoA is a marker of PPAR-alpha activation, and then aromatase enzyme activity as a sort of a hypothesized process that would lead to the Leydig cell tumors that were observed in previous studies within the male within the testis. And then lastly, the terminal evaluation, 104 weeks or 2 years, where we collected 40 plus tissues and looked for neoplastic and non-neoplastic lesions. And from here, I'd like to hand over to my colleague.
All right, so to continue the presentation by the NTP on the chronic and carcinogenicity studies for PFOA, Dr. Ron Herbert will talk about the NTP pathology review process. Dr. Herbert leads the pathology support group within the cellular and molecular pathology branch at NTP. He is a veterinary pathologist with over 25 years of experience in anatomic and diagnostic toxicologic pathology and pathology peer review of rodent toxicity and carcinogenicity studies. Dr. Herbert received his doctorate of veterinary medicine from Tuskegee University School of Veterinary Medicine and completed a residency fellowship and a PhD in anatomic and comparative pathology at the Purdue University School of Veterinary Medicine. Thank you, Dr. Herbert.
Thank you for that introduction, and good morning to everyone in the audience. I'm Ron Herbert, and I'm the pathologist of the NTP that was assigned to the PFOS study, and I was responsible for the pathology peer review of the study at the NTP. This morning, I will present an overview of the pathology evaluation process that the NTP conducts, and which is essentially the standard process that we follow for pathology evaluation of all of the NTP studies. Yeah. Okay. There are two phases involved in the pathology evaluations of the NTP studies. The first step is the study pathologist's review by a pathologist at the contract laboratory where the study was conducted. And the second phase is a pathology peer review performed at the NTP. This is a multi-step process that is under the direction of the NTP pathologist assigned to the study. Today, I will give a brief overview of what happens at the study pathologist's laboratory in step 1, but most of my talk will be centered around step 2, the pathology peer review process, which occurs at the NTP. For all the studies, for all the pathology evaluations, the NTP follows an internationally accepted set of best practice guidelines for conduct of toxicological histopathology evaluations, which were established and published by the Society of Toxicology Pathologists and published in our Journal of Toxicology Pathology. No. Okay. So this slide shows the publication of best practices that we follow in evaluation of the toxicological studies that the NTP does. Okay. Now, the first step in the evaluations of our studies is performed, is a study pathologist review, which is performed at the contract laboratory that conducted the study. The study pathologist is responsible for supervising the necropsies or the autopsies of the animals, for the initial microscopic evaluation of the organs and tissues, and for preparing a report of the pathology findings, which is included in the final study report. When the study report is finalized at the study laboratory, the pathology data are locked, which means that no additional changes can be made to the pathology data at the study laboratory. And then all the pathology materials and data are sent to the NTP archives, and then the pathology peer review process begins. Okay, the next step is the pathology peer review, and which is performed at an independent pathology laboratory under contract with the NTP and is directed by the NTP pathologist. This is a multi-step process, and it's a review of the initial histopathology and diagnoses and materials generated at by the study laboratory. And these materials and data are subjected to a rigorous, in-depth review that involves the several steps that are outlined in this slide. It includes the pathology data review, an audit of the pathology specimens, a pathology quality assessment review, a pathology working group review, and both of these are a review of the microscopic slides, and then subsequent to those reviews, audit of the data. Each of these steps is performed by highly experienced toxicological pathologists. Okay. The objective of the pathology peer review process are shown in this slide, and they are to reevaluate all positive findings in the suspected target organs and tissues. I take a very careful look at the precision of the pathology data, ensure that all treatment-related effects are properly identified, consistently diagnosed across all exposure groups, and correctly interpreted. And also to identify any pathology issues that may need to be addressed before the pathology data are finalized and reported. Okay? Okay. The overall objective is to establish confidence in the pathology data. So the first part of the pathology peer review process is called the pathology data review, which is performed by a second pathologist at another laboratory is under contract to the NTP. And this pathologist is known as a quality assessment pathologist. The pathology data review is a detailed review of the microscopic diagnoses, which are listed in the summary incidence tables for the study. And this is done mainly to confirm the suspected target organs and other treatment-related effects identified by the study pathologist, to identify any terminology issues that may need to be corrected before the data is finalized, such as inconsistent use of pathology terminology across the treatment groups, including the control groups, any errors in the terminology, and then any diagnoses that we may consider to be duplications. We also want to identify tumor incidences in the concurrent controls that may vary from the histological tumor data. We maintain a very rigorous database of historical controls for all of the strains of animals that we use, including mice. We will also review other records for findings that may have a direct correlation to the microscopic diagnoses, such as any in-life clinical finds, necropsy records, any macroscopic or gross findings, body weight tables, organ weight tables, and then any clinical pathology records. The findings of the PDR review are then documented in a report, which lists or details recommendations for review of a subset of organs and lesions during the next phases of the pathology peer review process, the quality assessment review and the pathology working group reviews, which I will describe in some slides shortly. The PDR essentially serves as a guide for these two reviews. The second step in the pathology peer review process is what is known as the audit of the past specimen, or the APS, which is essentially a quality control review of the physical specimens that are generated at the study laboratory. It is performed at the contract laboratory, again supervised by a pathologist. There is an audit of the pathology specimens from 10% of the animals to identify any problems based on the NTP specifications. For example, we will look at the preserved residual tissues in the tissue bags and examine them to make sure that all of the protocol required tissues and organs were properly sampled at necropsy. All of the lesions that were potentially gross lesions observed at necropsies were collected and properly sampled, and the identifiers on the tissue bags were correct. We'll also take a look at the tissue blocks and histology slides to make sure that they're all accounted and all present and accounted for each animal, and that the tissue blocks and histology slides were accurately labeled, labels are free of errors, and that the blocks and the tissues were properly prepared according to the NTP specifications. The results of this audit of past specimens is also now included in the pathology data review report. So the PDR is a document that lists 4 categories of recommendations for review of microscopic diagnoses during the quality assessment review, which is the next phase in the peer review process. These 4 categories are standard for each of the NTP studies. We review for all animals and all treatment groups, all tumor diagnoses that were made. For organs identified as treatment-related organs, we review all diagnoses in all animals, in all organs and tissues identified as a target. For all animals and groups, we will review specific diagnoses in specific organs, and we will review specific diagnoses only when that diagnosis was made in a tissue or organ. In this category, this last category, we'll usually address mainly any terminology issues that we have identified as problematic. So these categories, this list of categories, is standard for each NTP study, each evaluation for each NTP study. The only difference is that the organs and tissues and diagnoses that are recommended for review are not the same between studies. So for the PFOA, Here are the findings that were recommended for review based on the PDR. As you can see, it was quite an extensive review of the microscopic findings. Again, we looked at all tumors. In the second category, we looked at reviewed all diagnoses for the target organs. And for the males, those are the liver, pancreas, pancreatitis, kidney, and testes, which is shown on the left here. And for the female, here's the list of organs that we reviewed for all diagnoses. The third category, organs reviewed for specific diagnoses. For diagnoses of the male, these are the organs and the diagnoses that we reviewed. In the female, organs and diagnoses that we reviewed here. And then specific diagnoses for review. And again, these are mainly terminology issues. So possible diagnostic duplications, questionable terminology, and any unusual incidences any incidents in the lesions that we thought were unusual. So the next step in the pathology review process is the quality assessment review, which is a targeted microscopic review of the study pathologist's microscopic findings by now a second pathologist who was designated as the quality assessment pathologist. And this review, again, is based on the recommendations of the pathology data review report. The quality assessment pathologist reviews selected diagnoses to confirm the treatment-related effects, verify the accuracy of the diagnosis, make the terminology as consistent across all treatment groups in the study, and also ensure that the terminology is consistent with that used in other NTP studies so that we can possibly, in the future, compare results across studies whenever necessary. Also, if necessary, the quality assessment pathologist may further characterize the lesions or identify other lesions that may need to be added or some lesions that may need to be deleted from the study. Following the quality assessment review, any discrepancies between the study pathologist and the quality assessment and pathologist are either resolved by the NTP pathologist, in this case for the PFOS study, that was me, or during the next review in the pathology peer review process, the pathology working group review. So the pathology working group reviews is a final microscopic review of the diagnoses from the study and consists of two phases. The pathology working group pathologist review, or the PWG coordinators review, and the pathology working group review by a group of expert pathologists. The PWG pathologist review is an independent review of the slides by a third pathologist who reviews the same slide set reviewed by the quality assessment pathologist. So there's some redundancy in the system, but that serves for a complete in-depth review of the study. And the purpose of this review is to confirm the presence of treatment-related effects and diagnoses, resolve any outstanding differences between the study pathologist and the quality assessment pathologist, and then to select examples of lesions to be reviewed by the PWG panel of pathologists, which is the next step in the pathology peer review process. The PWG panel review is then the last review in the pathology peer review process. The panel consists of a group of pathologists who meet to examine glass slides with examples of treatment-related lesions. The panel review PFOA is chaired by the PWG pathologist or coordinator who leads the discussions. And the panel consists of the study pathologist, the quality assessment pathologist, the NTP pathologist for the study, and several other toxicological pathologists who are invited to participate on the panel. And these pathologists may be other NTP pathologists or non-NTP pathologists from other organizations who have not been previously involved in the evaluation. And these pathologists are highly experienced toxicological pathologists. The PWG panel review is the final confirmation of the pathology findings. The panel reviews examples of the lesions without knowledge of treatment-related groups, and by consensus vote, to confirm suspected treatment-related effects, resolve any outstanding diagnostic differences of opinions between the previous three reviewing pathologists, that is, the study pathologist, the quality assessment pathologist, and the NTP pathologist, and then agree or disagree on any new diagnoses that have been recommended by the quality assessment pathologist for addition to the study, or in some instances, agree on diagnoses that have been recommended for deletions. So following the pathology working group reviews, pathology data is updated to reflect the changes made during the quality assessments and the PWG reviews. The data then undergoes an audit by an independent contractor who was not in any way involved in the study prior to the audit. The data again is updated based on the audit results. And then the pathology peer review is considered complete when the final incidence and statistical tables are generated by the NTP and the data is posted to our website.
Thank you, Dr. Blystone and Dr. Herbert. We have a couple of questions, but we're running out of time, so I'm just going to take one of those questions. From Lanaya Volt Alexander, did NTP intend for this data to be extrapolated to humans? How does NTP recommend this data be used as point of departure in human risk assessment? Okay, so NTP does the hardcore science of looking at chemicals for carcinogenicity. They're not in the business of doing quantitative risk assessment. So I might add that for most quantitative risk assessments done either by EPA or Cal EPA or other agencies for cancer, the NTP bioassays are the data set of choice. Okay, I think we're on to our third presentation now, and we have Dr. Andrew Rooney here to talk about the NTP monograph on immunotoxicity associated with exposure to PFOA or PFOS. Dr. Rooney is Acting Director of the Office of Health Assessment and Translation in the National Toxicology Program at NIEHF. He's been actively involved in developing risk assessment methods and guidance throughout his professional career and is a principal author of the 2012 WHO IPCS guidance for immunotoxicity risk assessment for chemicals. Dr. Rooney has 4 years of experience in toxicology and risk assessment for the protection of public health. And for the last several years, he's been working on emerging issues in toxicology and environmental health, including methods to address study quality in terms of risk of bias for human, animal, and mechanistic studies, and adaptation of systematic review methods for addressing environmental health questions. Welcome, Dr. Rooney.
Thank you. And so as you can see on the screen, I'm going to be talking to you about the National Toxicology Program's monograph, or our evaluation of the evidence for immunotoxicity associated with exposure to perfluorooctanoic acid, or PFOA, and perfluorooctane sulfate, or PFOS. Okay, so you've already heard from Mohi. Oh, there's a delay, so I'm going to have to get used to the slide controls here. Give me a moment. You've already heard from Oiha on some of the background exposure information, but I'm going to cover it briefly. So in terms of exposure to the perfluoroalkyl acids, the PFAS, including PFOA and PFOS, have been used extensively in commercial and industrial applications over the last 50 years, and that includes as water-repellent coatings, and aqueous firefighting foams, and as lubricants. And PFOA and PFOS in particular have been widely used, and the exposure is essentially ubiquitous to residents of the United States and many parts of the world. The use and emission of these compounds, recognizing those high levels of exposure and the toxicity information we're talking about today, have been reduced in the United States and Europe through cooperative agreements. And it's because of a variety of factors, not just the toxicity, but also the persistence. These compounds are not metabolized, and they're not expected to degrade in the environment. There's a slower human elimination rate, and in fact, the half-life is on the order of 2 to 8 years in humans, whereas the half-life is in the order of days or weeks in other animals, including experimental animals. At the bottom of the slide, I'd like to draw your attention to some of the exposure data present in the NHANES surveys. The survey year is in the first column, and we take a look at the survey year of 1999 to 2000. The levels for PFOA in serum concentrations of residents in the United States, the mean serum concentrations for PFOA on the order of 5.2 micrograms per liter, and for PFOS on the order of 30.4 micrograms per liter. And over the subsequent years, for the latest year I have in this slide, from 2015 to 2016, those concentrations have gone down considerably. For PFOA, gone down from 5 to 1.56 micrograms per liter. For PFOS, from 30 to 4.72 micrograms per liter. So we know we have high levels of exposure, and for PFOA and PFOS, not just that we have exposure to the U.S. population, but they're also some of the highest PFAS, both in the environment and in human serum. Okay, moving on to the health effects evidence. I'll get used to the slides in a minute here. Hopefully we get back. Okay, so why evaluate immunotoxicity for these two compounds? That's because there is reports for exposure-associated changes for both PFOA and PFOS in multiple immune measures. Now, I'd like to highlight a few things on this slide. One, for both the experimental animal studies and the human studies, I've divided into 3 kinds of immunotoxicity because there's 3 major aspects of the immune system that should be evaluated separately. And that is immunosuppression, which includes evidence of antibody response, natural killer cell function, macrophage, a whole range of things. But those related events should be evaluated as one type of evidence. And then hypersensitivity. This might include things that you're familiar with, such as asthma or wheeze, airway hypersensitivity, eczema. And this is a different type of immune evidence and a different immune response, and so should be evaluated separately from the immunosuppression. And finally, autoimmunity. Again, a third type or major classification of immune response. So within the experimental animal studies, we knew that there was evidence for potential immunosuppression, hypersensitivity in terms of this increased immunoglobulin E or IgE and airway hypersensitivity, but there were no autoimmune studies that we're aware of. And there were similar reports in humans. Evidence that PFOA and PFOS exposure might be associated with immunosuppression, particularly the same types of evidence as in the animal studies, reduced antibody response, in this case to vaccines, hypersensitivity, higher levels of PFOA and PFOS associated with increased incidence of asthma and other outcomes in children, and evidence that higher levels of PFOA might be associated with autoimmunity, in this case, increased incidence of ulcerative colitis. So knowing that we had exposure and that we also had evidence of immune effects, the National Toxicology Program within our office, the Office of Health Assessment and Translation, considered conducting an evaluation of the evidence. Our office conducts literature-based evaluations to assess the evidence that environmental exposures, such as PFAS, cause adverse health effects. And the format of the evaluation depends on the goals of the evaluation as well as the extent of the evidence. If it was preliminary evaluation or a number of different exposures, there might be a systematic evidence map to see where there might be evidence to follow up on. Or for the specific research question or specific question, it would be a systematic review. And this evaluation format, once completed, would be communicated to the public, government, scientific, and medical communities in the forms of NTP monographs, shown on the screen here, NTP reports, potentially workshop reports, or publication in journal articles. I'd like to spend a few more moments talking about systematic review and evidence integration in our evaluation process. Basically, this is the state-of-the-art in terms of transparency, objectivity, and rigor in an evaluation format. And a systematic review is a predefined, multi-step process to identify, select relevant evidence, critically assess evidence, and then synthesize data from published studies to answer a specific research question. And the graphic on the right-hand side of the slide I'm going to use over the following slides to track our progress in the evaluation. And what it's laying out is the basic process of systematic review, 4 steps from planning and protocol. We're developing the specific research question, refining it, and developing a research protocol or an evaluation protocol to follow throughout the entire process. Performing a comprehensive literature search for evidence that might be relevant for answering that research question, selecting studies that are relevant and extracting data for answering that research question, assessing individual study quality in terms of risk of bias, and then finally the step for bringing it all together to reach a conclusion. You also note on the graphic on the right-hand side of the slide, there's 3 arrows going down. That's because for each step in the process, we evaluate the human evidence, potential animal evidence, as well as a mechanistic studies that might come from a variety of study designs. But the final step in the process is evidence integration. We develop hazard conclusions by integrating the evidence from the human and experimental animal studies with consideration of potential support from mechanistic data for biological plausibility. What might influence our overall conclusions? So given that process, for the PFOA and PFOS systematic review, we developed a web page to track our progress and developed a research protocol, a systematic review protocol for the entire evaluation, and posted it on that page, defining our objectives and our methods. That objective is to develop NTP hazard identification conclusions on the association between exposure to PFOA and PFOS and immunotoxicity. And just to note that conclusions were reached separately for each chemical, but due to overlapping databases, we thought it was advisable to consider both of them together. Again, emphasizing the rigor and transparency in the process, moving on from that planning and protocol development. The process for identifying the evidence began with a comprehensive literature search, as documented on this slide, also documented in the NTP monograph, where we identified over 5,000 references that were potentially relevant for addressing the question. We reviewed them for relevance and eligibility, tracking the progress, coming up with 148 studies that were then data extracted and assessed for study quality. This included 33 human studies, 93 animal studies. And then also emphasizing the transparent and objective process, we went through the procedures to extract the relevant data for assessing immune effects into a web-based project pages within the Health Assessment Workplace Collaborative, or HAWC project pages. And again, the lower right-hand corner of the slide lists the website. So not just the NTP monograph is published, but also the web pages associated with the data extraction for bibliographic details, for study results. And then moving to the process of evaluating the evidence, we also assessed individual study quality in terms of risk of bias and posted that within the project pages and within the monograph. The next step in the process is to move from the individual studies to look at bodies of evidence. That's essentially a jargon term for grouping studies, grouping results on the same or similar outcomes, considering those main categories of immune response introduced earlier in the presentation for immunosuppression, hypersensitivity, and autoimmunity. I just want to emphasize that within these bodies of evidence, we focused on the best evidence, evidence for immune-related diseases and measures of immune function. And the next step of the process is to begin the evidence integration, bringing the conclusions together across the human and animal bodies of evidence. And the first step of that is to rate confidence in that bodies of evidence, and that confidence rating is a measure of how confident you are that the findings from a group of studies reflect the true relationship between exposure to a substance and the effect. And the confidence ratings are developed within a grade framework, a widely accepted framework used for both human and animal studies, including for medical interventions. They perform separately for the human and animal bodies of evidence on an outcome basis, starting with an initial confidence rating based on study design features. Whether a given experiment used controlled exposure, whether it assured that exposure was prior to outcome, individual outcome were present within the study, and a comparison group was used. For well-conducted experimental animal studies, they would have all four features and start out at a high initial confidence. And then we would systematically consider factors that may increase confidence in that body of evidence, perhaps potentially evidence of a large magnitude of effect, or evidence of a dose response, consistency across multiple species, etc. And then factors that may decrease confidence, unexplained inconsistency. For example, some studies show an effect and others do not, or risk of bias, problems with study quality, or indirectness, where you're concerned with something like antibody response, but you only have evidence of T cells and B cells that are associated with antibody response, but they're further upstream from the measure. So I've been talking a lot about the methods so far, and I'd like to move on from methods to some of the example bodies of evidence. And so here's a body of evidence from the animal studies on the PFOA, or the potential for PFOA exposure to be associated with changes in antibody response. And for this body of evidence, there were 7 experimental animal studies that reported consistent suppression of primary antibody response in terms of immunoglobulin M, or IgM, in mice associated with higher levels of PFOA exposure. And this is figure D6 from the NTP monograph, and also within, can be found at the Hawk website indicated earlier in the presentation. I'd like to orient you briefly to this figure. For the individual rows, they represent different studies or experiments that might be reported in the individual studies, with the doses of exposure to PFOA listed in individual lines. And then what's graphed is the control results for the antibody levels, and then a percent change relative to control for the animals that were exposed to PFOA. So the blue circles and the dotted blue line represent the control values, and then the other circles represent animals that were exposed to PFOA. And what you can see is a change, or percent change relative to control, that the dots, the data, move to the left. And that is reduced antibody response, or reduced antibody levels in animals that are exposed to PFOA. So higher levels of PFOA result in a movement on that graph to the left, evidence of a dose response, and reduced antibody production with higher levels of PFOA exposure. Within that body of evidence, with this consistent suppression of the antibody response, we also looked at reasons for upgrading and downgrading our confidence ratings, potentially upgrading or downgrading. And we noted that there were some concerns on study quality, and made a conservative choice to downgrade for potential risk of bias concerns, including a lack of reporting of blinding within the outcome assessment, but also reasons to upgrade our confidence, including evidence of this dose response as indicated on the slide. So overall, we had a high initial confidence. We considered upgrading and downgrading and ended up at that high final confidence in the body of evidence and a high level of evidence. I'm going to show you now the human body of evidence. And for this, there were 4 prospective studies and 2 cross-sectional studies that reported suppression in one or more measure of the anti-vaccine antibody response associated with exposure to PFOA at different life stages, whether it was prenatal exposure levels, childhood, or adult exposures. And with that body of evidence, there were, after considering the factors for potential upgrade and downgrade, there were no changes in for factors that may influence our overall confidence. And we started out with a moderate confidence based on study design factors and ended up with this moderate level of evidence from the human studies. And hopefully I'm getting to the next slide. I am, okay. Moving back to our methods, the last step and really in performing this evaluation, the one that we're most excited to get to, is what does it all mean when we bring it together? And what conclusions could we develop that are supported by the data? This evidence integration, where we combine the evidence streams to develop our overall conclusions. The initial hazard conclusion is developed by considering the human and animal evidence together, and then a final conclusion is reached after considering the potential impact of mechanistic data and biological plausibility of the effect. It's done with this figure on the right-hand side of the slide. On the y-axis, that's the level of evidence from the human studies, and the x-axis is the level of evidence from the animal studies. In both cases, going from a low or inadequate level of evidence to moderate, and then a high level of evidence. I'll illustrate this with that same PFOA antibody response data in the following slide. So the human level of evidence from the antibody response resulted in a call of moderate level of evidence from the human studies, the human body of evidence on the y-axis, and the animal body of evidence is a high level of evidence, reaches the conclusion of presumed to be a hazard to humans. And we step back and consider the biological plausibility. Specifically, were there data that show PFOA-associated disruption in events associated with the process of forming an antibody response? Particularly if there is early events, changes in B cells or T cells or cell signaling cytokines necessary to form the antibody response, antigen processing, etc. And I'll tell you that after we reviewed that evidence, we did find some association with PFOA, but it was not at concentrations, lower concentrations or the same concentrations where we observed the antibody response. In order for it to precede and be associated with a mechanism that explained the result, it had to happen at a lower concentration to be able to explain the biological plausibility for the outcome. So in this case, we found the data supported our hazard conclusion of presumed, and there was no change. So the final conclusion was presumed to be immune hazard to humans for PFOA. And I'd like to make a statement on both exposures at this point. We reached the same conclusion of presumed to be immune hazard to humans for the PFOA and PFOS. There were similar bodies of evidence for both chemicals. And in fact, most of the epidemiological studies included measures of both PFOA and PFOS, and that each compound supported the suppression of the antibody response. Now I'd like to look at a couple of the other major categories of immune response, particularly hypersensitivity-related outcomes. At the top of the slide, again, going with the human body of evidence, there were 6 prospective cohort studies that evaluated PFOA and PFOS, or potential exposure to PFOA, PFOS, and hypersensitivity-related outcomes. Most of these studies reported no effect, or with higher levels of exposure, there were decreases in outcomes such as asthma, eczema, wheeze, or immunoglobulin immunoglobulin E, IgE, which is associated with hypersensitivity, or overall measures of total allergic disease. So higher levels of PFOA and PFOS weren't supported for causing hypersensitivity. They were associated with no effect or potentially lower levels of hypersensitivity-related outcomes. However, for the 5 cross-sectional studies, or case control studies with a cross-sectional exposure, these were in children aged 10 to 19, there are two separate patterns that we observed in the results. That PFOA exposure was associated with increases in hypersensitivity-related outcomes, increases in asthma, total IgE or rhinitis, and PFOS, the results were inconsistent. Some studies reported an effect, others reported decreases in asthma, wheeze, or IgE associated with PFOS exposure. So these two chemicals may have different outcomes and different mechanisms for hypersensitivity-related events. Concentrating first on the PFOA, where we have the more consistent evidence, we found the body of evidence supported low confidence and a low level of evidence. And for the animal body of evidence for PFOA, there are two studies in mice that also reported higher levels of PFOA associated with increases in hypersensitivity, in this case, airway hypersensitivity. And we reached the conclusion of moderate confidence and moderate level of evidence. Again, using the blue box for the summary of the outcome-specific data for PFOA, there was a low level of evidence from the human studies and a moderate level of evidence from the animal studies. For PFOS, is it inadequate evidence to support conclusions due to the inconsistent results in both the human and animal studies? And one more of the major outcome categories for immune-related events, and that is the autoimmunity-related outcomes. Starting again with the human body of evidence, there were two studies, in this case from the same population, the population of the Ohio Valley. You may have heard of the C8 studies. This is a population with high levels of PFOA exposure relative to most parts of the world and relative to the U.S. population, certainly. And these studies reported PFOA-associated increases in an autoimmune disease of the colon or rectum, that is ulcerative colitis. There were mixed results for rheumatoid arthritis and no evidence of association with PFOA exposure and other autoimmune diseases they tested. In the first analysis, they looked at both workers and residents to support this association with ulcerative colitis. In the second analysis, they looked at workers only. This is reported in the Steenland studies from 2013 and 15. And overall, given that this was a single population, there were no data on other populations, and there was concern that the studies reported results from both workers in both analysis, and that worker data could have suffered from co-exposure to other chemicals in the work environment and the potential for confounding, we had low confidence in the data, a low level of evidence, and unfortunately there were no animal studies to be able to use in reaching conclusions. So for the autoimmunity for PFOA, that was a low level of evidence from the human studies. There are no animal studies, and for PFOS, there were no studies reporting association with autoimmunity. So I know there's a lot of methods and a lot of results, but in the end, what I'd like to highlight is the conclusions of the monograph for the two chemicals. For both of the chemicals, for PFOA and PFOS, we found that they are presumed to be an immune hazard to humans, and this is based on the high level of evidence that PFOA, in this case, suppressed the antibody response from animal studies and a moderate level of evidence from the studies in humans. And this is supported by additional, although weaker, evidence. For PFOA, that evidence is primarily from the epidemiological studies that PFOA exposure is associated with increased hypersensitivity-related outcomes, increased autoimmune disease, the ulcerative colitis. And then I didn't outline the data here, but also some evidence that it's associated with the reduced infectious disease resistance. And the evidence that PFOA exposure is associated with multiple aspects of the immune system supports the overall conclusion that PFOA alters immune function in humans. Now, when it gets to the next slide, you may not notice because the top half of the slide is essentially the same. For PFOS, the conclusion again is that PFOS is presumed to be an immune hazard to humans, and it's based on this high level of evidence. In this case, that PFOS suppresses the antibody response from animal studies and a moderate level of evidence from the human studies. But after that point, the results were different and the studies were different. And this is supported by additional, although weaker, evidence, primarily based on experimental animal studies, that PFOS exposure is associated with suppression of disease resistance and suppressed natural killer cell activity in animal studies. And those are several related endpoints for immunosuppression. And so it's interesting that all the PFOS evidence ended up with immunosuppression, and there's different types of immune evidence from PFOA. The overall conclusion, again, the evidence from multiple aspects of the immune system supports the overall conclusion that PFOS alters immune function in humans. And with that, I'd like to highlight at the lower right-hand corner of the slide, I guess that's where you should always look for web links on my slides, to get to the NTP monograph and look at the results in detail. And I'd like to thank OEA for the opportunity to present today, and the audience for tuning in. And I don't know if we have time for questions, but certainly we're all still here in the room here.
Thank you, Dr. Rooney. We do have time for one question. This was submitted by, where are we? Ali Hamadi. It says the PFOA decreasing in the blood. Since PFOA and PFOS appear to be decreasing in the blood of the general population, do we know that others have been increasing? So that's one question.
So I don't have, certainly the exposure patterns are changing, but I have not looked at the concentrations of the other PFAS relative to PFOA and PFOS going down, whether others are going up. Perhaps somebody else on the phone?
For the ones that are being measured, in general, they're either staying flat or going down. But obviously, there's a whole new amount of them that are being added to the class, and I don't think the assessment is clear on. There is exposure to them, so those are all going to be brand new. Likely, they're measuring blood levels now to see what they are.
Okay, another question from Shauna Clark. What can be said about extrapolating the animal data for PFOA antibody response to relevant human vaccines, where disease-specific vaccines were variable in antibody response, e.g. negative for measles but positive for mumps, rubella?
So the overlap of the antibody response data from the animal and human bodies of evidence is considerable. So I would say that the animal data is predictive of potential immunotoxicity in humans. Now, the differences between different vaccines may be the efficacy or the potency of the different vaccines. It may be different aspects of the antibody response that are triggered by different vaccines. And it may be the individual studies that looked at exposure at different times relative to boosters. So all those factors go into the human studies and complicate the ability to understand the data. And that's why we are particularly, careful to evaluate the whole body of evidence, not a single study. And the epidemiological studies indeed looked at multiple populations, multiple vaccines, multiple timings of exposure, and give us that overall conclusion from the human studies, and then it's bolstered by the animal studies. So it's a big picture question, and I think that's a really astute question to ask.
Okay. Another question from Raj Sharma. Would the outcome still be presumed if the human data were inadequate?
So the high level of evidence from the animal studies for the antibody response would end up probably at suspected rather than presumed.
Okay.
That's one level lower on our scale.
Okay. Then another question from David Mellard. Does the NTP monograph provide no AELs and low AELs for the various studies cited?
Excellent question. So the NTP monograph, and so our evaluations look at hazard. And I think that the OHIA speakers earlier were pointing out that we didn't do a risk assessment, we do a hazard assessment. And so the no ALs and low ALs are cited for the individual studies in the discussion for human relevance and in the discussion comparing the animal data to what's known about human exposures.
Great. I think that's all the questions we had for NTP. Thank you so much, all three speakers, for participating in our webinar. We really appreciate it. All right, I think we're scheduled to take a break now. It'll be a short break. Please come back at 11 o'clock.